Before I begin, so roughly in the audience, raise of hands, how many people are familiar with quantum outside of these talks? Okay, so about 10% maybe, so that's great. I tailored this specifically. A lot of the details are abstracted away, swept under the rug, so if you want to find out more, there's a paper that you can go to, but hopefully it should be tangible. So my name is Evan Anderson. You can find me at EJD Anderson on various places, or just Evan, or if you really want to email me, my email's down there. All right. So I split this up into sort of 4 sections. The first and the last are going to be pretty brief, but I think they're still worthwhile. So I'll talk about myself for a bit. And then we'll talk about what is covert communication. We're not even going to talk about quantum covert communication in this section. But the next one, we'll add the word quantum to it, and there you go. And then finally, we'll talk about some of the ethical considerations of this work and just quantum technologies in general. Okay, so about me, I have always been interested in information, from how we communicate, the words we use, to digital information, sharing it across the internet, to books, the philosophy of what an idea is and how that forms in people's minds. And more recently, I've found out that there's a deep connection to physics in terms of entropy, and that just sort of blew my mind. All right, so before I did what I do now, I worked as a software engineer for a few years, and I really wanted to build a better internet and be an advocate for open information before sort of the enshittification has happened to the internet and commercialization. But that's a completely different talk. So as a hobby, while I was a software engineer, I was getting more interested into physics and sort of what could be done. And eventually I decided, maybe I should try, working in quantum. And during that time, I went to a number of conferences, talked to a number of people in industry. This was roughly 5-6 years ago. And I wanted to work in research, and ultimately, sort of the direction they all pushed me was, you really need a PhD to do this. I think this is much less the case now. I think there are very much avenues for hobbyists or people just, software engineers doing control systems or whatnot to get really involved in quantum research and, in industry. So I think there's a few people here from IonQ, maybe Xanadu, that could probably answer, are there jobs for people who don't have quantum background in quantum? And the answer is yes. All right, so I'm a PhD candidate at the University of Arizona in the College of Optical Sciences, and this is also the home of the Center for Quantum Networks, which is a National Science Foundation-funded engineering research center. So there's a 10-year goal to build the quantum internet, and we're in year 5, but it's basically a collaboration between many universities, and it goes from everything from building sort of the error correction codes that would go into this to building the devices that would actually send the qubits long distances. All right, so let's talk about what is covert communication. And so first, let's talk about what covert communication is not. So if you look at this picture, you sort of squint your eyes, maybe cross your eyes, a shark will pop out. And this image is called an austereogram, or if I think these were popular in sort of the 80s and 90s in the malls, where a 3D image pops out if you look at it just right. And so this is sort of hiding an image within another image. But if you have the right mask, you just sort of slide over it, you can recover the shark pretty easily. And so this sort of falls under the concept of steganography, or what I might call sort of hidden communication. Another example of this is, say you have a newspaper. I'm the journalist, I write an article, and the newspaper gets distributed, but I tell my friend, hey, I sent you a secret message, or a hidden message. Just read the first letter of every word in this article I wrote. And another common one is least significant bit steganography. So this image on your left is what might get distributed, might get sent through a communication channel. But then the receiver, who has confidential information, knows that in each of these pixels, they're represented by 8-bit strings, or RGB. If they take the least 2 significant bits of each of those pixels, normalize it, they'll get a cat picture out the other end. And so this is great, but of course, if an adversary knew this technique, this is a pretty common technique, so they probably do, they could also extract the cat image. All right, so the previous examples, we were sending a signal and then hiding another signal or another message within that signal. Can we hide our signal without relying on that pre-existing signal? The answer is yes. Otherwise, you guys came here for nothing. And this is what covert communication is. Another name for it might be low probability or vanishing probability of detection. And when we talk about this, especially in the research context and information theory context, a lot of security protocols, schemes, they typically have an adversary called eavesdropper Eve. And so her goals typically are maybe to capture and read secure messages, or unsecure messages, just simply intercept the signal going through. Might be doing traffic analysis just to see who's sending information to who and at what time and for various nefarious reasons. Or maybe even just message tampering. So they intercept the message, they decode it, they then change the message and forward it on to its original intended party. And that can be, hey, send your money to this bank account instead of this bank account. But if Alice and Bob know that there's some message tampering going on, that's still an issue because this undermines trust within the channel itself. Okay. But that is other things, other protocols. In the covert communication sense, we talk about a warden whose colloquial name is Willie. And he really only has one goal, and one goal only. And that's to detect whether or not Alice is sending Bob a message. In the work that I do, we allow this Willie to have access to the start time, the duration of the transmission, the method of encoding, so that could be the frequency, dual rail photons, what have you, and perfect quantum devices. So that could be a fault-tolerant computer that as many qubits as he wants, perfect quantum memory, perfect quantum detectors that are theorized to be able to work, but no one can actually build them. And ultimately, Willie's probability of error comes down to a coin flip, so that's this 1/2 here, minus the probability of him making a false alarm call, where that's Alice and Bob are not communicating, but he raises his hand and says, you guys are communicating. Plus the probability of a misdetection, and that's Alice and Bob are communicating, and Willie guesses, I don't think there's any communication going on. Okay, so covert communication is fundamentally governed by something called the square root law. And so the average power per channel use must follow 1 over root n, where n is the sort of number of channel uses. So you can think of this maybe as time bins if you're sending a pulse of light as a 1 or a 0. And this effectively allows for m qubits in root n channel uses. And so this diagram on the bottom is fantastic clip art. What we have is Alice and Bob, they have this pre-shared secret that they have before communicating. There are some ways around this and more details that won't be in this talk, but if you want to talk about this pre-shared secret, catch me after this. And then they're transmitting through some channel. And there's noise in this channel. And then there's a warden in the middle somewhere that raises his hand and is trying to detect whether or not communication has occurred. Okay. So that's covert communication in a nutshell. So now we add the word quantum to it, and we're sending qubits instead of bits. So a lot of this talk will be coming from this archive paper, which just was accepted for a conference and is going to be in a journal. It's a little bit old, but there'll be an updated version soon. And so what we do is we encode our quantum states in dual rail photons. So we have represented our 0 and 1 as logical states. And physically, these correspond to two mode states. So a 0, 1 for our logical 0, and a 1, 0 for our logical 1. And furthermore, we need a quantum channel to do quantum communication. And so we do this with the lossy thermal bosonic channel. And we also allow Willy the aforementioned sort of all-powerful quantum devices that physics allows. Okay. So first, let's talk about the lossy thermal noise bosonic channel. And so this is really nice because we can represent this channel as just a beam splitter. And so what is a beam splitter? Yeah. So if A and E sort of represent the input modes, so this is A for Alice, E for the environment, so that would be the noise. And then B and W are the output modes, so Bob and Willy. There's this eta, it kind of looks like an N term. And there's a relationship between these input modes and output modes that's given by eta. So eta sort of is a between 0 and 1. And if you're not familiar with these annihilation operator, creation operator notation, basically what eta does is says a fraction of Alice's signal goes to Bob, some other fraction goes to Willy, and similarly a fraction of the noise goes to Bob, and the other fraction goes to Willy. That's roughly it. It's a little bit more complicated, but that's all you need to know. And then the thermal noise part of this is we have a thermal state, which again is represented by this mathematical formula where these K's are in the Fock basis. But again, you don't really need to know much about that. The only thing you really are worried about is this NB. So when NB is larger, so NB can go to infinity, that just means there's more noise in the system. So a completely noiseless system, NB would be 0. And so this channel is fully characterized by this eta term, which sort of is called the transmittance, so how much Alice can transmit to Bob, and this noise term, NB bar. Okay. So this picture is a more complicated version of that clip art that you saw earlier. So this channel here in the middle is equivalent to that beam splitter. So you could imagine just taking that beam splitter and putting it right there. We got one input arrow here, two output arrows there, and if you want to make it completely equivalent, you would have a arrow coming in from the top that represents the noise, but that box just sort of encapsulates all that. And so I previously mentioned this pre-shared secret. This is the only part of the system that is unknown to Willy. And again, he knows the photon frequency that we are encoding our qubits in. He knows that we're using dual rail qubits. He knows when we're going to transmit, if we're going to transmit, and the duration. And again, we give him access to this perfect quantum detector. He also has access to quantum computers and all that, but they don't really help him. And so there's this additional line that wasn't on the previous figure. And if there's a classically covert communication channel available, so where Alice and Bob can send just bits between each other, they can improve the number of qubits that they can transmit between each other. I'll talk about this a little bit later. So let's zoom in on each of the other parts of this diagram. So there's nothing covert about Bob. All he's trying to do is do some local operations, and then there's an encoder-decoder pair, which does some sort of quantum error correction code. And he uses all that. He receives a state that Alice sent, and all he's trying to do is make the best estimate he can, this M check, for the original message that Alice sent, the M. And so in reliable communication, sort of in information theory, all this means is that as the number of channel uses goes to infinity, the error between this estimate and the original message should go to 0. You know, how you categorize that error there's a number of different ways, but effectively you let the number of channel uses go to infinity and you recover the state completely. Otherwise, it's a pretty good estimate. And so this is how classical communication, reliable communication, works as well. All right, now zooming into Willy. If he uses a quantum optimal detector, so this is a joint detection receiver, and what that means is he performs a measurement across all n uses of the channel. So these dual rail photons with their quantum error correction code might have entanglement between each other. And so he doesn't want to measure them one by one. He wants to effectively measure them all at once so we can capture those quantum correlations. And the mathematical formula that comes out of that is, it's described as the Hellstrom measurement, is this 1/2, again that's that coin flipping term, minus 1/4 times what is called the trace distance between these two states, a sort of rho naught state and a rho 1 state. And so rho naught would be the state that Willy receives when Alice and Bob are completely silent. They're not transmitting anything. So Willy's just capturing noise, effectively. And so we're subtracting off the state that he captures when Alice and Bob do transmit. And we'll basically wrap this term up in a variable we call delta. And so this delta term then measures the amount of covertness that Alice and Bob have between each other, right? So if ideally delta should be 0, so Willy's probability of error is equal to 1/2, just a coin flip. And in that case, right, these two terms would just be equal to subtract. Okay, and now Alice. We saw that Bob was trying to get an estimate for M, and before Alice sends it through the channel, she does some encoding, and she does that with dual rail qubits and a quantum error correction code. Again, if you want to talk about that quantum error correction code after, it'd be great. Then over n uses of the channel, Alice decides whether or not she wants to transmit. And that's a fraction Q. So basically, what that means is this little knob goes from, do we transmit vacuum or do we transmit some message at a rate of Q? And so which of the Q times N channel uses are used by Alice and Bob constitutes as this pre-shared secret that Alice and Bob have. And so, for example, if we have 100 channel uses, Alice and Bob might choose, hey, I'm going to send you a message in 5, the 10th time bin and the 100th time bin. And so Bob knows that, but Willy does not know that. So effectively, Bob has to average over that entire 100 channel uses. You can't specifically just throw out everything except for 5, 20, and 100. And we also require that the Alice to Willy channel be entanglement breaking. And so She can have some special device that she uses. Again, I can talk about that after if anyone wants, to make that actually happen. And so what does this all sort of culminate to? And it's this single equation. So again, Q was the amount, or the fraction of the channel uses that Alice and Bob use. And it is a function of eta. So again, that's the transmittance of the channel between Alice and Bob. NB bar, which was the total noise in the system. The square root of n, which is the total number of channel uses. And that delta parameter. Oops. And so ideally for covertness, you want to make Q as high as possible because that way you can get a larger throughput. You're using more of the channel uses for more of the signal. And so how do we actually make Q larger? Well, if we increase eta, that would increase the numerator and then make that larger. We can also have large noise in the system and small n. So this delta factor is actually predetermined by Alice and Bob. So they could choose 0.05, and that's the amount of covertness they are. They could choose 10 to the minus 9 and be more covert. And so this is somewhat at odds with reliable communication, which they still want to do. They just want to do it covertly. So ideally, their throughput, they'd be using every channel use to transmit some part of the signal instead of just a small fraction of it. They still want a large eta because, right, you still want most of your photons to get to Bob and not Willie. And you want small noise, right? You want your signal to noise ratio to be small so you can extract more information out of fewer uses of your channel. And you also want large n, but n here is a little bit inconsequential. Okay, so now that's sort of the theory of everything. And so now we've actually modeled what this might look like in free space optics. And so here, what I'm plotting is the photon wavelength versus channel parameters. So on your left-hand side, this is the transmittance. Oh, sorry. Let me back up, actually. This model is something called the mod-tran model. And this models the transmittance and noise on a clear day where Alice has a transmitter the size of, I believe it's 10 centimeters. Bob has a receiver that's the size 10 centimeters. And they're separated by 10 kilometers. And so Alice would shoot a laser, for example, between them through free space. And so free space optics, the transmittance and the amount of noise in the air, whatever, is dependent on the wavelength, right? Because this band here, where you see the transmittance go to 0, I believe this is the methane. So methane in the air absorbs 5 to 8 microns. And then this is the CO2 band. And then as you get higher and higher, you get water vapor being primary absorber. And so the background noise in free space optics typically comes from black body radiations, right? So the sun's very bright. And so it's emitting incoherent light, which is thermal. And the Earth is warm. And so we're also getting light or radiation from the Earth that contributes to this noise. And if you recall, for covertness, you wanted large eta and you wanted large NB bar. So these are sort of at odds for each other for specific wavelengths. And so typically your telecom wavelengths are 1.55 microns. And so you want high transmittance, low noise to do reliable communication. But it looks like maybe for covert communication, you might want to actually act in that regime, the sort of 10 micron range. And so now what we can do is plot the wavelength of our free space optics scheme versus the amount of covert qubits and bits. And so there's an upper bound, classical covert bits, and a lower bound. And I'll talk about each of those individually. So the classical covert bits are in green here, and so This is sort of what we'd expect. We're using a integration time of 60 seconds and a modulation frequency of 10 to the 9th, so gigahertz. And this is the number of qubits, or sorry, the number of bits that we can send covertly. And so this is actually pretty low, right? So typically your reliable number of bits should be on the order of your time bandwidth product, which in this case would be roughly 10 to the 10. And so we're only getting 10 to the 3 covert bits. Now this upper bound on the number of qubits and lower bound on the number of qubits. The lower bound is a scheme using dual rail photons, which we just talked about, and Alice and Bob having that classical covert communication link between each other. This upper bound is a bound that doesn't assume any specific type of encoding. It sort of emerges from a different, emerges in a different way where you don't have to have a specific type of qubit encoding, you don't have to use a specific type of quantum error correction code. And so the fastest you might be able to do, or the most number of qubits, in reality might lie somewhere here. But we know that we can do at least this, and we can know that it's not more than that upper bound. And what you'll notice is missing from here is the sort of one-way bound where we don't have that classical communication link between Alice and Bob. And the main reason for that is Alice, when she breaks entanglement between her and Willie, that introduces additional noise or additional loss into the system, and that prevents Bob from actually reliably recovering the original message that he sent. So if we loosen up some of the restrictions on Willie, say he doesn't have a all-powerful quantum receiver, instead he just has maybe a photon detector or photon number resolving detector. In that case, his detector breaks the entanglement between Alice and Willie. And now we can actually plot that one-way bound because now entanglement is broken naturally between Alice and Willie. She doesn't need to introduce additional loss. She doesn't need to introduce additional noise. And so here I'm just plotting basically the parameters, putting those graphs side by side from what you saw earlier. And again, we have this sweet spot where there's some transmittance and some noise, and that corresponds to the maximum amount of covert quantum information we can send. Right, so I just talked about free space optics, but the quantum internet is likely going to exist in fiber, and it's likely going to exist in fiber that already exists, it's already laid. And so it will coexist with classical signals that we already use today. And so fiber is not known to be particularly noisy by itself. It doesn't get the black body radiation from the Earth, it doesn't get the black body radiation from the sun, but we can think of other ways that noise gets introduced into the system. And so one of it is Raman scattering. So if you have a classical pulse propagating through your fiber, that pulse interacts with the fiber itself, makes the fiber vibrate, the vibrational modes. And for the most part, a lot of the light that comes off of those vibrations looks exactly like the light that we originally sent. So that makes sense because that's what we want. Long distance, we want the same light that we input, the same light we get output. But a little bit of light gets scattered with wavelengths that are shorter and wavelengths that are higher than the original pulse. And whereas this green light achieves the same coherence, so say I have a specific polarization, this green light has that same polarization. The light that comes out of the red or the blue, that's thermal light, that's noise. And so we can hide our signal underneath the noise generated by this effect. And so haven't built anything like this yet, so this is sort of the next thing that we're going to look at. But there has been 2 covert experiments ever, as far as we know. And this is one of them, but this was doing classical communication. And so I won't go too in depth here, but this is sort of a tabletop version of it where you have a 10-kilometer spool of fiber, you have some classical signal being pumped into the system, and then you have a covert classical signal pumped into the system. And so you could imagine that a covert quantum system would look almost identical to this, except for the covert signal that gets pumped in is now dual rail photons or something of that nature. All right, so that's great. So moving on, why should we actually care about covert quantum communication? Why should we care about covert communication? Would banks want it? Would companies want it? I mean, it sounds really cool. You can prevent detection of your signal. You don't necessarily need encryption. You could also layer encryption on top of it, but if it's not detectable by some adversary in the first place, you don't need that. The problem is that, let me go back actually. The problem is that these numbers are very small when you actually compare it to non-covert. So this is sort of the throughput almost of the system. And so the amount of information you can send is, say you have a 56K dial-up modem, divide that by 100. I don't know what that is, but that's roughly the data rate you can get with covert communication in systems that already exist. So free space optics, fiber. If you had artificial noise, you could probably get higher, but typically that's not the case. All right. So really, there's only one application for this, and that's military, right? You're in a war zone. I want to communicate to someone. It doesn't necessarily need to be super fast, or it doesn't need to be a super dense message. And I can do it covertly. That's great. I don't alert someone to my position. You can also do something like covert quantum radar or covert quantum sensing. But again, maybe someone here has a better idea of what it could be used for, but everything that I've come up with is, only the military. And so this is sort of really at odds with why I wanted to do research in quantum in the first place. I thought quantum is this amazing technology that's going to change the world for the better, and it might. But it also has potential uses to, enhance oppressive military regimes. And I could go about, I just don't want to work on this at all. But as I've talked to more and more people, other students, professors, Joan, who's here from the Quantum Ethics Project, begin to understand that it's important to have people be a part of the conversation who don't necessarily want to use the technology the way the military wants to use the technology. They might go ahead and do it regardless, but to be a part of that conversation is very important. It can shape policy, and it can also just alert people to, hey, they have the power to do this, they might be doing it. So that's sort of what I want to end on. If you have any questions, feel free to ask now, or I'll be around for the rest of the time.
Brilliant work. All right, we do have plenty of time for a few questions. Are there any questions from the floor? Yes, come up here, please. If you have another question, please queue up behind him. Brilliant talk.
Thank you.
Really well done. All right, here we go.
Why wouldn't the use be for dissidents, like Tor?
Why wouldn't it be for what?
A dissidents. Like someone in a repressive regime that can't communicate. Oh, like I need to talk like Yeah.
Yes.
Yes. Okay. So why wouldn't it be useful for dissidents, for someone in a repressive regime like Tor is?
Yeah, that actually is a very good point. So the question was, why would this not be useful for dissidents, someone who is in an oppressive regime, to use this technology? And the answer is, you're right. That would be a use case. I think it's much more likely that a military would use it to oppress versus someone having access to a quantum device that could, do covert communication. But yeah.
Next question.
So, do two people need to observe the quantum, a quantum bit simultaneously in order to effectively read the message?
No. So the question was, do the two people, you're talking about Alice and Bob specifically, do the two people need to read the quantum message to extract the information from it? And the answer is no. The message at the state of the qubit at Alice will be lost when Bob receives it. And so this is the idea of no cloning. And so just only Bob needs to read it.
So just Bob needs to read it, and he can effectively transmit a bit of information that is useful. Is that correct?
Sorry, could you repeat that?
Yeah, so only one of them, Bob would need to read it and collapse the wave function in order to extract useful information.
Yeah, so that's a good point. The question was, only Bob needs to read it to collapse the wave function and read the information. And so the short answer is yes. What Bob does with the qubit beforehand is maybe more important. So you could do something like super dense coding, where you're sending more information in a qubit than classically, but Bob could then use, say, Alice has a source that can generate entanglement, can generate qubits. Bob doesn't have a source. But what you do with those qubits might be some sort of imaging, sensing, and whatnot that Bob can take advantage of. And so he's the only one that needs to actually do the measurement. Alice doesn't need to do anything in this case.
Could we use the double slit quantum eraser setup to send a message into the past?
The question was, could we use the double slit quantum erasure setup to send information into the past? And I think the answer is no. I will not say I'm quite an expert on that question, but I will say
We'll be
no.
checking the math on that
Yes.
in due course. The whiteboard session for that is tomorrow morning, 8 a.m. Last question.
Thanks for speaking today. And I didn't quite understand in the example that you gave where Alice is communicating with Bob and she's using either light transmission through open air as a medium or potentially through fiber. What exactly makes that communication quantum? Because in the example, it just seemed like she's sending light as a signal. Bob is receiving it. I didn't really get it.
Yeah, that's a good point. So she doesn't necessarily... Let's look at this picture. So if she can just send, classical messages, so these are called coherent states of light, she can send that covertly, sort of at this rate that's in green. If instead, let's go back here. So what we're saying is, instead of doing that, she is sending sort of a quantum message, so this superposition state, through the channel. And so the idea is that Bob will receive a qubit. What he does with that qubit, we don't really care in our analysis. But really what we're looking at is sort of what is the rate, what is the sort of throughput of sending quantum messages instead of just classical messages.
All right, well, can we please give a one round of applause to Evan, please? Thank you.